Hello. In the last video, you learned about the basic properties of megavoltage photon beams. And now that you know that, we can go and focus on how these beams are actually used to create a plan in a patient. A patient is often not treated with a single beam or multiple beams, and how are beams combined, and what are the considerations behind that when you do treatment planning. So, obviously treatment planning is a big art that takes months, years to really master. But and so that's not the intention of this video. But this is just to give you a flavor of this and give you a basic introduction to the principles behind treatment planning. Here we go. You'll remember this curve. This is the percent depth dose, the PDD, plotted versus depth. This is for a single beam. Like I say, we don't often treat with a single beam. So let's look at a slightly more realistic plan. This is two fields combined together. So these are two opposed fields, let's say an APPA, AP plus PA. You can see the isodose lines on the left, and then the plot on the right is a profile to the center of the beam going from the top to the bottom. So what you see is basically a superposition of two PDD curves. So the curves look like this, and you can imagine if you combine two of them together, overlay them, add them together, this is the shape you get. So to deliver a dose of 100 at the middle, right there, you actually end up delivering a higher dose near the surface. In this particular case, it's twice as high as the dose in the center. So there's an inhomogeneity inside the patient. You can reduce this inhomogeneity in various ways. One way is to increase the energy of the beam. So here I'm showing the blue from before. That was a 6 MV beam. But now if you use an 18 MV beam in green, you see the hotspot is greatly reduced. That's because the penetration is higher. Essentially, the PDD falls off less quickly for an 18 MV beam. When you superimpose them, it's more homogeneous. And the same effect will play out for the other factors that you've studied. For example, the field size dependence. A large field size falls off less, and so it has less of an inhomogeneity. Now let's look at what this might look like in an actual plan. So here is a pelvis plan where you're doing beam from the left, beam from the right, two beams together, and you see if I draw a profile through here like that, here's the curve, just like I showed you in the previous graphs. Now this is a 18x plan. If I go to a 6x plan here, again, same right-left laterals. So you'll see that you get more of a hot spot near the surface and soft tissue for the lower energy beam, the 6x beam, the one in the dotted lines, versus a higher energy beam, the 18x in solid. Now let me describe another effect. That's the dependence on thickness. So in blue here, I'm showing a two-field plan for a thickness of 50, or separation of 50. You see if for a dose in the middle of 100, you have to give a dose out here of 200. That's the one I showed before. Now for 20, it's much more homogeneous. And for 10, more homogeneous still. So basically this inhomogeneity depends a lot on the thickness of the patient. So that has some practical implications. So for example, it's going to be much more inhomogeneous in, say, a pelvis or abdominal plan than a brain plan, and you could use a lower energy beam, 6 MV, say, to treat a whole brain, where you would want to use like an 18 MV to treat a pelvis or an abdomen. So the final thing I want to talk about for a minute is the use of multiple beams. So up until now, I've just been talking about these simple two-field plans, parallel opposed beams, for this case from the right and the left. But I'm not restricted to that. I can use more beams than that. So here I'm showing a four-field plan, so beams coming in from AP, PA, right, and left. So let me draw a dose profile through here, right to left, and you'll see that this four-field plan in dots has quite a different dose profile than the two-field plan. In particular, lower doses in the peripheral regions. You see that here as well, where the peripheral regions have a dose now below 70%, or much higher before, and also the central tumor region is covered much more homogeneously. So that's a general principle of planning. By using more beams, you get lower doses to the surrounding tissue. An extreme case of that would be stereotactic radiosurgery, where we'll see in later videos that you sometimes use hundreds of beams. Alright, so now I want to walk you through another case scenario that's going to lead into another planning principle. So let's consider that we're going to try to treat some kind of superficial tumor here, a circle. There's no tumor on this image, it's just used for an example. So you want to treat the sphere to an even dose. So we could consider applying the principle that we learned before, using parallel opposed fields like this. And here's what the dose would look like. This would not be a very good approach because you would get a very high hotspot in the left region of the patient. So you could consider another approach. Let's take a beam from the right and then a beam from the AP direction and combine them like this. And here's what you get. And this is closer, dose to surrounding tissue is lower, but the dose is not very homogeneous in the tumor. That's because you have the two beams combining here near the entrance to give you a high dose, and when they combine down here near the exit, they give a much lower dose. So you want to get this more homogeneous. So this brings me to the topic of wedges that can be used to modulate the fluence over the beam. So let me explain what those look like through some cartoons. So let me start here with a simple open field, a 20 by 20 field coming down onto a flat phantom. You can see the isodose lines here. They're pretty even. Now let's put the wedge in. So here you'll see this wedge. It's a physical device, and it causes one side of the beam to be cold and the other side to be hotter. So the wedge has a toe side and a heel. And the toe is thinner and the heel is thicker. So the dose on the heel side is going to be lower than the dose on the toe side. We often talk about the wedge angle. That is defined as the angle through which this isodose line tips relative to the horizontal. So a higher angle wedge is essentially just thicker at the heel than at the toe. And so the isodose lines tilt more. And so here are some examples: 15, 30, 45, 60 degree wedges. You can put whichever wedge in that you need. So when I talked about Linux before, I kind of glossed over the wedge aspect of things. They can be implemented in different ways by different vendors. So let me show you what that looks like. So one vendor puts the wedge down here at the bottom. That's a physical device, a piece of metal, different size pieces, 15, 30, 45, 60. The therapist comes in and out of the room and puts that piece of metal in. The other one is up here in the head of the machine, and it can move in and out. So because it's not accessible outside the room, there has to be some electromechanical system to move it in and out when you need it and don't need it. Also, because of space constraints, there's only one physical type of wedge in this system. It's the 60 degree wedge. And to get different angles, you use combinations of open plus wedge beams to get the angle that you need. There are other solutions as well to get a wedged profile in a beam. You can have the dynamic wedge, in which case a jaw is swept across the field. And if the dynamics of that are done just right, then you can build up dose in a profile that looks like a wedge profile. And again, you can change the angle as needed. So there are different solutions. So let's go back to this planning problem that I started out with. And you can see here, it should be pretty obvious how a wedge might be used. So here we go, let's put them in. So here is your two wedges. and you'll see that they cool off the beam in the heel part of the wedge and give you a much more even dose distribution. Actually, this was a little bit under wedge. This was a 45-degree wedge, and I found when I was playing with this particular plan that a 55-degree wedge worked best. So here it is. Wedges have many different applications, and you'll explore some of those in the problem sets. So there are a couple of rules of thumb about wedges that are probably worth knowing. So if you have two beams like this coming out, you always want to orient the wedges so that the heels are together. Heels together, toes out. Also, you can figure out the angle of the wedges should be. So if there's some angle here between the beam, let's call it phi, then I can figure out a rule of thumb for what the wedge angle should be. How big should the wedge be? 15, 30, or so on. The wedge angle is equal to 90 degrees minus phi divided by 2. So you can work that out by thinking about what it takes to make the isodose lines sort of match, come parallel to each other. So here's an example. If phi is 120 degrees, then the wedge angle is going to be equal to 30 degrees. So there we go. Those are some of the basic considerations in treatment planning. There's more, obviously. I'm going to leave you with some further reading, some suggestions. And in the next video, we'll dig a little bit more into how treatment plans are done in a patient. Thank you.